G'day chemistry students. In this video, we're going to be covering dot points 4.1.1 and 2. We're going to be calculating some enthalpy changes in this video. Let's get into it. So let's first talk about this idea of enthalpy. Now, enthalpy, it can be written as delta H, which is here on this exothermic profile diagram and here on this endothermic profile diagram. Essentially, it is the energy change as reactants move to products in a chemical reaction. So my first example over here, what we see is that there is a drop in energy, that the reactants lose energy in an exothermic process. That energy is being released to the surroundings. That means that the change in energy, the enthalpy, will be negative. There's a drop in energy. Over here on this side though, the reactants gain energy by the end, which means that the enthalpy has increased. It's taken in energy from the surroundings, meaning that the energy of the products at the end is greater. So enthalpy, as I've alluded to, refers to the loss or the gain of energy in a chemical process. Notice that we label it delta H, and the delta part is a Greek letter, and when we use it in mathematics, we usually refer to it as a change in. Essentially, that means a difference. So delta H here is the difference in energy between reactants and products, and here delta H is the difference again between reactants and products. If we're taking a difference, if we're subtracting one from another, that begins to explain why we have positive and negative values. It's always products minus reactants. Note as well, the energy of the reactants and products is very difficult to measure. So we can't really stick, say, a measuring device like a ruler or a thermometer into a chemical reaction and be able to measure its starting and ending energy. That's quite difficult. There's no real instrument that's able to do that. What we can measure, though, is the change in energy moving from reactants to products. So even though we might not know what the energy of the reactants are or the energy of the products, we can measure the change in energy as it moves from reactants to products. In fact, that information is probably a lot more valuable to us anyway, and it's certainly easier to measure. Note as well, enthalpy is written as delta H and is measured usually in joules. That's the SI units that we use. Note as well, a lot of the time we'll be using a term called molar enthalpy. So molar enthalpy is the energy change that's happening in a reaction per mole of substance that's either reacting or per mole of substance that's being produced. This is a much more valuable measurement than just regular enthalpy and energy change, because we can use it to compare energy changes for different substances. So for example, let's say I was burning two different fuels. I could measure the amount of energy that's being produced by both of those fuels and compare them per amount of mole that's been burnt. Note as well, molar enthalpy is written as delta H as well. Usually we'll have some sort of subscript that I've just written as X, which will refer to either the substance or the process that is occurring. So for example, if I was burning ethanol, for example, I could write delta H and in the subscript write the formula for ethanol or write down ethanol. If we're combusting ethanol and we're finding the enthalpy for combustion for ethanol, we could also write down delta H for combustion or something like that. And molar enthalpy is measured in joules per mole. Now, usually when we are doing some sort of experiment to measure enthalpy, or in particular molar enthalpy, we undergo or undertake a process called calorimetry. Essentially, what we're doing is measuring delta H by finding a temperature change in the water. So we might undergo a reaction that's in a insulated cup of some description. We can mix the water around to make sure that the temperature is even, and we can measure the temperature change that's occurring in the water. That temperature change in the water can then be calculated to the amount of energy that the water is absorbing or giving away to the reaction, and we can use all of that information to calculate delta H. That's going to be the main focus of this video. Now we are going to do a few pracs using calorimetry and applying the mathematics. I'm going to go through sort of the equations that you need to get that calculation done, as well as a practice calculation in this video. It's just a first look. We'll be doing these calculations in context with a couple of chemical reactions in class as well. So note that when we're calculating changes in energy, the formula that exists on our data sheet is this one here. It's commonly known as the MCAT equation. but it's that Q is equal to mc times delta T. So note that C is a constant similar to, say, the Avogadro constant that we've used before, or the gas constant that we used in the PV equals nRT equation. Here, C is the specific heat capacity for water, which is a really important one that I'm going to be getting into in the calculation and the coming slide. So, Q, first off, is the energy change in a substance. So, for example, if we're doing our calorimetry from a couple of slides back, Q would be the energy change in the water. So either energy that's being absorbed by the water or energy that the water is giving away. So we can calculate that energy change in joules. M is the mass of the same substance, which is measured in kilograms. And delta T is the change in temperature of the substance. So for example, if I was burning a fuel and the water was absorbing that energy, we could measure the amount of energy that the water has absorbed, assuming that we know how much mass of water we've got, and we can measure the temperature change in the water. Now, all of these variables, Q, M, and delta T, are all kept in check by this C value, the specific heat capacity of water. So that's down here, 4.18 times 10 to the 3 joules per kilo per Kelvin. Now, note as well that we measure T in Kelvin. I've just missed that on my slides, it looks like. I'll update that for our final version. But delta T is measured in Kelvin. And we need to make sure that we are substituting in values for Q, M, and delta T that match the units of C, the specific heat capacity of water. Now, in particular with the value C, the specific heat capacity of a substance is different depending on what the substance is, depending on whether or not it's a really good conductor or a really good insulator of heat. Now, depending on what's absorbing energy, this value will be different. Generally, we'll be using the specific heat capacity of water for our calculations. If you ever need to do a problem that uses a different substance instead of water, you'll be provided with that specific heat capacity within the question itself. Otherwise, the expectation is that you're using your data sheet to find that information. Now, keep in mind that changes in energy for reaction are determined by heating or cooling water, as I've alluded to already, and that's measured as Q. Now, what I want to keep in mind is that Q is going to be the polar opposite of delta H. So, for example, if you are undergoing an exothermic reaction, delta H is a release of heat. And a release of heat means that heat is being lost in the reaction. So delta H would be negative, meaning that Q, the energy of the water, is going to be the opposite, the polar opposite, meaning that Q is going to be an increase in energy, meaning that Q is positive while delta H would be negative, or vice versa. Note as well that the molar enthalpy of a substance, in these kind of calculations, you need to know what Q is. And because we're finding the amount of energy released per mole, you also need to know the amount of substance that was reacting or that was produced. Now, these equations will make a lot more sense in context, so I'm going to flip straight over into our calculations, show you a practice one, and then we can do the rest in context when we are doing our calculations for our pracs. Now, you're going to find that video in part 2 because this video has gone long enough as it is, so I'll see you in the next one.